Hi there, welcome to your lesson on derivatives with sine and cosine. And just in case you didn't know, math puns are the first sign of madness. Alright, this is exciting. In this lesson, calculus and trigonometry come together and the result is fun. Let's get ready. This is going to be great fun. Alright, here we go. So here's a sine curve. And our goal is to find the derivative of this sine curve. Let's do this step by step. Don't forget, derivatives represent the slope of a graph, right? So we're going to do this point by point. Here's going to be our derivative of our sine graph. First question, begin with when will the derivative be equal to 0? In other words, when does this graph have a slope of 0? And let's forget about the negative part. Let's look at just from 0 to 2 pi. When is there no slope on this graph? Okay, there is no slope here, right? We have a horizontal tangent line. There's no slope here. Also horizontal tangent line. Therefore, our derivative there will be 0, and our derivative over here at 3 over 2 pi will also be 0. Okay, so those two values are derivatives of 0 because the slope is 0. Okay, next question. What is the slope before pi over 2? So now we know here the slope is 0. What's happening before pi over 2? What kind of slope do we have there? Well, the slope is positive, right? We can see a positive slope there. Therefore, the derivative value must be some positive y value here. Okay, next question. What is the slope after pi over 2? So now looking at this original graph, after pi over 2, what's the slope over here? Well, the slope there is negative. So that means after pi over 2, we must have a negative derivative value. So maybe somewhere down here. Okay, next question. What happens after 3 pi over 2? So we know again at 3 pi over 2 there's no slope. But what happens after 3 pi over 2? What kind of slope do we have there? Well, it's positive again. See, positive slope, positive tangent line. Therefore, after 3 pi over 2, positive. Now, at x equals 0, what's the slope at x equals 0? So like right here, what do you think? Well, here's the amazing thing. At that point right there, the slope is exactly 1. That line has exactly slope of rise 1, run 1. So the slope will be 1. So we're here. And guess what? At 2 pi, same thing. The slope at 2 pi is exactly a slope of 1. So at 2 pi, slope of 1. Interesting. What do we have going on here? What is happening? What is that? Oh my goodness. I can't believe it. That's the cosine graph. So that means the derivative of the sine graph is the cosine graph because the cosine graph represents the slopes along the sine curve. This is incredible. So what about cosine? You're probably wondering now, what about cosine? So here's cosine. We know the cosine curve looks like this. Let's do a couple points here as well. So what's the derivative of cosine? Let's take a couple points as well. When's the slope 0? Again, when's the slope 0? Well, we know there's no slope here. So the slope of 0, and we know there's no slope here. So at pi, we also have a derivative value of 0 because there's no slope there, no slope here. Okay, and then the slope here is negative. That means, oh, sorry, also at 2 pi, no slope, no slope. Okay, and in here, the slope is negative between 0 and pi over 2, or actually between 0 and pi, it's a negative slope. So negative slope. Here's another negative value. And I put that at pi over 2. So at pi over 2, there would actually be a line with a perfect slope of -1 right here. And then we have a negative slope because it's still negative here. Then we get to 0 slope. Now over here is positive slope. So I have a positive value. And then at 3 pi over 2, guess what? Perfect slope of exactly 1 right there, 1. And then slightly less positive slope. Hey, what have we graphed? You might be thinking, wait a minute, the derivative of sine was cosine, so that means the derivative of cosine must be sine, right? Wrong. This is not the sine graph. Look at it. The sine graph begins here, yes, but it goes up and down. So what is this? It looks like the sine graph, but the sine graph should go up and then down. Oh, this is a reflection of the sine graph. So the derivative of cosine is actually negative sine x. Also amazing. So now you know. So calculus, trig functions coming together, the perfect combination. If we have original function sine of x, the derivative is cosine x. If we have original function cosine x, the derivative is negative sine x. And tangent, by the way, has this derivative. That one, I don't think it's in this course anymore. It's in the old course. So let's focus on these first two. Let's memorize those. So there they are. Derivative of sine x is cos x. Derivative of cos x is negative sine x. Memorize those. Hint. In our text, it gives us this hint that these derivatives are only valid when we measure in radians. Why? Why can't we use degrees? Here's an answer for you. Degrees are a discrete unit of measurement. In case you didn't know, we don't give degrees with decimals. If you wanted to say, for example, 2 degrees and some little portion of the next degree, we actually show it like this. Maybe you're not familiar with this, but this says 2 degrees, 5 minutes, 30 seconds. That's how we write degrees. We wouldn't write 2.3 degrees. That doesn't work. Degrees are written this way. So degrees are a discrete unit of measure. We cannot go to infinite decimal places with it. Therefore, in calculus, it's something we measure to an infinite level, right? We need continuous functions to look at calculus. So radians are a continuous unit of measure. Radians we can break down to any fraction, any irrational number. So therefore, it works out. Okay, so now you may be thinking, I want to prove it. We just found out the derivative of sine x is cos x and the derivative of cos x is negative sine x, but prove it. So how are we going to prove it? Well, let's prove it with this joke. It says, I'm a bit worried about Mike, this guy here, his obsession with the difference between sine and cosine. Don't worry, it's just a phase. Why would they say that, and why is that funny? Because that's referring to the idea that sine and cosine graphs are just translations of one another. If you translate a sine graph, you get a cos graph, and likewise. And that kind of shift, translation horizontally, is called a phase shift. So we'll come back to this proof later, if you're interested, at the end of this video. All right, flashback. We just learned these two rules of derivatives. But now we're going to combine those with some other old derivative rules. You may remember the chain rule, everybody's favorite rule. When you have a function within a function, to take the derivative, you take the derivative of the outer function, keep the inner one like it is, and then multiply by the derivative of the inner function. That was the chain rule. There was also the product rule that tells us what to do when we have a multiplication of two functions. And there was also the quotient rule. What do we do when we have division of functions in terms of finding the derivative? We're going to use these rules in conjunction with these new rules. So this is going to be lots of fun. Let's get started. So here's the first one to try. Try A, B, and C here. And so you know, I'll give you hints along the way. For B and, sorry, not C, B and D. For B and D here, you will need to use the chain rule. So let's try these three. Let's see how they go for you. And now let's check the answers. Here's A. In A, you simply take the derivative of the first piece, which is cosine x, and the derivative of the second piece, which is negative sine x. There, we found the derivative. Easy. All right, just piece by piece. Second one in B, in this case, this needs the chain rule. Like I said, you're going to do the outside function first. Wait a minute. Yes, the outside function, so the cosine function. And the derivative of cosine is negative sine. And we leave the inner function unchanged. And then we multiply by the derivative of the inner function. That's the chain rule. And the derivative of t squared is 2t. And that simplifies to this. See that negative there, 2t, there we have it. Okay, take a close look at it. Pause if you need to. It's simple, but it's also important that you understand that. And in D, same approach. We have a function within a function. Remember, when we have a cube here, that means the same as having a cube on the whole sign. So now the outer function is something cubed. So when we take the derivative of the outer function, we bring the 3 down, we leave this as it is inside there, and we reduce that exponent by 1. Then we multiply by the derivative of the inner function, and the inner function is sine of 2x, and the derivative of sine is cosine, so there's cosine of 2x. But then we have a function in there as well, so this is actually double chain rule. Super exciting. We have a function within a third function. So again, outer function multiplied by the derivative of this one, but this one also has a function in there, so now multiply by the derivative of that, which is this 2. And then it simplifies that. Great problem. Again, pause and just study it. Think about it. It's awesome. All right, here's some more to try. Try A to begin. Check your work. Again, that's a simple one where we just do a derivative of the first part, derivative of the second. all right, using our derivatives of sine and cosine. Now, for b, you will need product rule, because we can see one function times another. So here's product rule. And also for b, when you're simplifying the result of b, once you've taken the product rule, you want to simplify it. Remember this double angle identity. You will use that to simplify. So let's try. Okay, here's b. Check your work carefully. Product rule, and then simplifying it. Notice that this has been rewritten like this because of this double angle identity that we learned in the last unit. All right, let's try C. In C, you will need the chain rule. Okay, there's a function within a function. We can rewrite it like this to begin. Take the derivative of the outer functions. That means derivative of sine. So here we have that. Derivative of sine becomes cosine. Leave the inner function. Multiply by derivative of the inner function. So derivative of that is this. Simplify that to this. Great job. Try D. In D, you will need chain rule, and again, you will need this trig identity to simplify it at the end. Let's try. Okay, derivative using chain rule. Rewrite this like this. Derivative of that, drop the 2, leave this unchanged, then multiply by derivative of the inner function, which is cosine x, so like this. It becomes this, which by this double angle identity can be simplified to this. Great job, let's keep going. Okay, A, how are you going to do it? In A, you will use the quotient rule, but you're like, that's not a quotient. But wait, we're also going to use one of these identities, the tangent one. So rewrite tangent as sine over cosine first, and then use the quotient rule. Let's try. Okay, there it is. That has been rewritten like this. Using the quotient rule, check your work against the rule real carefully. Simplify it. To simplify it, we also use one of the identities. So first of all, we use that one I told you right there. And then secondly, here, notice this numerator became 1. And the reason is because we used the Pythagorean identity to simplify this into 1. So this is getting a little complex, but you can do it. I know you can do this. Let's try another one. In this one, the second one here, you will use the product rule. No, you will not. All right. It might look like product, and you can use the product rule. If you want, you can do it as a product of two functions. You can try. However, with this one, it's even easier. Notice that this actually matches one of our trig identities, our double angle identities. So why not simplify it first and then take the derivative? But of course, if you want to, you can use product rule. But you will need chain rule as well. Let's try. Okay, so here it is. That can simplify to this, using one of our double angle identities. Then take the derivative of that, outside function times derivative of the inside function. There we have it. Great work. Let's keep going. Try this one. In this one, notice there's e, and in this one, notice there's ln and ln. I have to remind you about the rules of those. Remember, the derivative of e to the x is e to the x, and the derivative of ln x is 1 over x. So use these rules in here. Okay, in part A, you will also need the chain rule. Let's try. Okay, check your work. Notice when we took the derivative of the first one, it remains unchanged, but we multiplied by 5 because that was chain rule. We need to multiply by the derivative of that upper function. And second one, we also use chain rule. Derivative of sine is cosine, but then we had to multiply by the derivative of the inner function. Okay, try B. In B, you will need the product rule. Let's try. Okay, check your work for B. Pretty simple product rule problem. C, you will need chain rule. Check your work for C. Okay, great. Let's keep going. I have 4 more for you. Try these 4. Let's see how they go. You'll check your answer in a moment. All right, these will really tell you if you're getting the hang of this. Check this carefully. Pause, because I'm going to move quickly now. So check your work carefully here. How did it go? Okay, last one. You're going to find the equations of a tangent line and a normal line. Oh my goodness. I can't believe you're doing this to me. Yes, yes I am. Tangent and normal lines. Remember how to find those? Let's try. Let's try. Try your best and then check your work. Here are the solutions to that. Pause, study it carefully. You can do it. What a great journey. I told you we'd come back to the proofs, but we'll do those later.